So in our talk, essentially we will be considering the transfer problem in mission analysis. So we'll be considering a spacecraft, this is like a particle, under the influence of several gravitational bodies. And the problem essentially is that the orbit of this spacecraft, say, it's in this way, and we want it to go to a specific target, for instance, like an orbit like this. And this should be accomplished by means, say, of some delta V, some maneuvers at some points of the trajectory. See? So we will need essentially some maneuvers at some points of the trajectory, and usually in mission analysis one wants to design the trajectory in such a way that some index is optimized. Usually it could be time, or could be usually delta V, so the sum of the delta V's be minimum. Okay. So in order to go to the background, I again go to the same guy as Elizalde. Emily told us about Newton. The Newton in 66, he discovered the law of gravitation and some other things related with fundamental calculus. And these things were published in the Principia, it was in this year. And as Emily told us, there were some very celebrated laws. The first law of Newton, second law that most likely you know, so I'm not going to describe these laws. But essentially we had the second law and the law of the universal gravitation that merged together. It's the fundamental equation of mechanics. The force is equal to mass times the acceleration. And the law of universal gravitation, which tells us that the force is proportional to the product of the masses and inversely proportional to the square of the distance. And this was very important at that time because in some way Newton unified what happened in ground and in heaven. So this was a nice thing of the theory. So the motion of the planets is the same motion as if you have a stone and you throw a stone in the ground. Okay. Using these equations, one can set up the equations of the two-body problem. In the two-body problem, we essentially can describe the motion of a satellite about the Earth, or the motion of a moon about a planet, or the motion of a planet or asteroid about the sun. Okay, and the equations look like this, and this is a simple application of Newton's equation. You have two bodies under the influence of their mutual gravitation, and so we wrote the first equation, force equal mass times acceleration for one body, or for the second one. This problem can be seen that it's equivalent to the central force field problem that in the Newtonian case has this equation. So what I mean essentially is that the motion of one particle above the other one, or of any of the particles about of the center of mass, follows an equation like this, where mu is a certain constant. Okay, so this is the differential equation of the Newtonian central force field problem that can be integrated thanks to the conservation of some fundamental quantities, the energy and the angular momentum. As probably you know, all the solutions of that equations are conics sections. So we can have ellipses, in particular circles, parabolas or hyperbolas. So these are the equations of motion of a body with respect to another one, or a body with respect to the center of mass of a system of two bodies. Okay. So based on this, Walter Hoffmann in 1925, before the space era, he designed a way to change the trajectory. Assume that we have here the Earth, for instance, and we have something orbiting, a satellite orbiting the Earth in a circular orbit. And we want to transfer the satellite from this orbit to an outer one, a bigger size, for instance. So what we can do is just to put a delta V here, a maneuver, and this maneuver injects the satellite into an ellipse, and when we arrive here, we we do another maneuver in which we can insert the satellite in this outer orbit. Walter Hohmann find that an optimal way to do this is by means of connecting these two orbits by an ellipse whose perigees and apogees were tangent to the inner or outer orbits. Okay. So this is simple, and this is essentially what space agencies do when they want to transfer satellites from inner orbits to outer orbit about the Earth. Okay. But the same procedure can be used in order to transfer satellites from, say, orbits of planets. So for instance, we have here one planet, say the Earth, and here we have another planet, say it's Venus. This is both are about the Sun. So we can transfer from this one to this other one using the same procedure. Of course, we need to phase the departure and the arrival. So since we have a time, there will be a fixed time for the trip. Okay. And then you have to phase everything in order that when you launch here, you will find the other planet in the right position. Of course, but this is essentially the same transfer, but you have a phasing problem as well. But it's not difficult. The thing is that when the satellite approaches the outer planet, the influence of this planet, the gravitational influence on the satellite, could be much bigger than the one of the Sun, and the same could happen here in the neighborhood of the Earth. So, in order to deal with this problem and to design, say, complex missions, one introduces the sphere of influence. The sphere of influence was introduced by Laplace in order to compute the trajectories of the comets approaching Jupiter. He knew that when a comet, when it's inside the solar system, most of the time the trajectory of the comet is related, say, by a conic, essentially by a conic with respect to the Sun. But when you approach Jupiter, things are not so easy. I mean, the gravitation of Jupiter disturbs the motion, and so it's no longer, say, a motion with respect to the Sun, but a motion with respect to Jupiter. So for instance, if we consider this sphere of influence can be computed with a given law, say, and one can find, by using the argument of Laplace, a sphere, for instance, about the Moon, where when you send a space probe from the Earth, when it's inside the Moon, when it's inside the sphere of influence about the Moon, you take into account only the Moon. And when it's outside this sphere of influence, you take only into account the gravitation of the Earth or the gravitation of the Sun, in case if you are in the planets. So this provides a way to design missions known as the patched conic approximation. Essentially, this patched conic approximation divides the space into various parts, and by assigning each of the bodies, the Sun, the planets, the moons, the sphere of influence. When the spacecraft is within the sphere of influence of the smaller body, then we consider two-body problems with the spacecraft and the smaller body. And otherwise, we consider the influence of the satellite with the Sun or with a larger body. And the method is called patched conic, because at the boundary of the sphere we need to patch these conics in order to have, say, that the solution of these uncoupled two-body problems merge. Of course, this is not a real solution of the vector field given by the gravitation attraction of all the planets. It's not a solution, but this can be taken as initial seeds of further numerical refinements. So we need an extra numerical procedure once we have this, but one can compute transfer trajectories this way. Okay. For instance, for a lunar mission, we proceed this way. We observe the sphere of influence. We consider the Earth gravitation inside the lunar sphere. We consider the Moon's gravitation. And at the border of the sphere, we patch the conics in order to get a patched solution. So this is the Moon, this is the Earth, and this is the sphere. So essentially, this is the arc of a conic. And when we are here, we patch the V infinite, which is the velocity of escaping, say, from the Moon, because the sphere of influence is like being at the infinite distance in some way from the moon. So things are patched in order to have the orbit that comes to the moon be the same one in a patched way with the outside one. So it's essentially it's a conics exercise. So one considers incoming velocities, things like this, and the incoming velocities have to be connected with the escape direction of the hyperbola about the moon and things like that. In this way have been designed many all the interplanetary missions. All the interplanetary missions have been computed, say, by initial patched conics approximation, and then numerical refinement using full ephemeris as optimization procedures. For instance, some missions like this, Rosetta of the European Space Agency, that after launch, it was 03, had several RAFs and several encounters of Mars flyby and Earth flyby and so on, and accomplished the target some way. Cassini is a mission to Saturn, interplanetary mission to Saturn, and it was computed in the same way because one has to have into account that there is no way that the probe at its own power can reach the Saturn. So you need the gravitational influences of Jupiter or other bodies in order to send a satellite from the Earth to some place far away like Jupiter. It's not possible. You will need a huge rocket with a lot of fuel that is impossible to be launched from ground. So you need this encounter with the planets in order to design this kind of interplanetary solutions. Another one is the Voyager trajectory. It was intended for the study of the outer solar system. So there were two spacecraft that in 1989 they crossed, say, the border of the solar system, and now they are just deep space. Well, but this is what we need for everything. So, but the thing is that there are cases that things are not always so easy, and this is the first one is the three-body problem. The three-body problem, as you can see, is a problem that cannot be solved in an analytical way. Okay, so we cannot find solutions, and sometimes this is well, some cumbersome. Okay. So mathematicians have been worrying about solving this problem, and of course there is no way to solve this problem as has been proved, but we can say many things using this problem. But really this problem is, we need to use this problem, or it's not necessary at all, because we can design interplanetary missions patching two-body problems. We don't need that, essentially. There are certain cases that you cannot do these patched conics, and these special cases are the one related with the Libration points that we are going to see in a moment. It was essentially places on the sky where the influence of the sun and the influence of the Earth, for instance, are of the same order of magnitude. And so if you maintain the satellite there, if you want to maintain the satellite there, it's under the influence of the sun, and also it's under the influence of the Earth. So both appear in the same way. So for this purpose, we consider the restricted three-body problem. The restricted three-body problem considers was essentially introduced by Euler in the 18th century, and Jacobi also did many computations with this problem. Essentially considers the motion of a particle under the gravitational influence of two mass bodies, two main primaries. And we put this, in order to visualize things in a relative way, a nice way to consider this problem is putting the two primaries fixed on the x-axis. So we consider the motion of the particle with respect, is a relative motion with respect to the position of these two particles. So in our restricted three-body problems, we will be considering P1 and P2 moving in circular orbits around them. Okay, and we consider a reference system where at the x-axis, this one here, is aligned with the primaries. So this could be, for instance, the Sun and Jupiter, or the Sun and Earth, or the Earth and Moon. Okay? And the x-axis goes this way. The y-axis is inside the plane of the motion. It's 90 degrees in the sense of the orbits of the primaries, and the z-axis is orthogonal to the plane of the motion. So all the pictures that I'm going to show from now on will be in this reference system. So things will be somewhat different that we are used to see, because this is a non-inertial reference system. Okay, the questions of motion are these ones, where these terms takes for the Coriolis forces, and here omega. These are the partial derivatives of omega, which is effective potential. We consider the centrifugal potential plus the gravitational potential. Okay. It's interesting to say that these equations have a first integral. Is the Jacobi constant. That we define it in this way. This is a function of positions and velocities that is preserved on the trajectories of the equations. The restrictive body problem has also a Hamiltonian representation. This is the Hamiltonian. And also, in fact, the Hamiltonian is the Jacobi constant. So in fact, the same. Well, another ingredient that we are going to use was initiated by Poincaré, the qualitative theory of ordinary differential equations. Since this problem is not solvable under, say, quadratures, what Poincaré tried to explain is how these solutions can behave in a qualitative way. Without knowing explicitly the solutions, try to say things about the properties of these solutions. Another ingredient is the Libration point solutions, that probably are the only ones that are essentially known explicitly, the solutions of this restrictive body problem. They correspond to equilibrium solutions, L1, L2, L3, L4, and L5. They are in the ecliptic plane, if we consider Sun and Earth. And they correspond to places where the gravitation of the Sun plus the gravitation of the Earth balances, and with the centrifugal force. So everything in the non-inertial frame, all the forces acting on a satellite located at this point here balance, and you have an equilibrium solution. It's a equilibrium solution of the differential equations. Okay. We have 5. And we mostly, in this talk, we will be considering these 2 points, L1 and L2. L1 is between the Earth and the Sun, for instance, if we take Sun and Earth, and L2 it's behind the Earth in the line of the Sun-Earth. So here we have again another representation. This is a planet. We have the Sun, we have the Earth, and here we have these 2 points. The position of these 2 points can be expanded in powers of the mass parameter of the restrictive body problems. I forgot to say that the restrictive body problems depends only on 1 mass parameters, and the dimensions of units, time, and the units of distance and time and masses are dimensional in some way. So it turns out that the restrictive body problem only depends on a mass parameter, and you can convert, say, any system, Sun, Jupiter, Sun, Earth, to this restrictive body problem just by means of computing the mass parameter of the system. And then once you have solutions in this restrictive body problem, you can translate into, say, the physical system by means just of suitable conversions of coordinates. Okay. For instance, in the Sun-Earth system, the distance between L1 and L2 and the Earth is of the order of 1.5 million kilometers. Is of this order. essentially it's 1/100th of the distance between the Sun and Earth, which is 150 times 10 to the 6 kilometers. So essentially this distance is 1/100th of this distance here in the solar system. So why we need to go to these liberation point orbits? The thing is that these liberation point orbits are easy and inexpensive to be reached from the Earth, and they provide good observation sites of the Sun. For instance, the L1 is between the Sun and the Earth, so you can do the Sun observation, and at the same time you can send the signal of the observations back to the Earth, align it in the same position. Essentially, all the properties of the liberation points are good because of this nice configuration, these relative configurations, and you can take word of these relative configurations. At L2, it's very good for space observatories because you provide a constant geometry for the observation. You have always the Sun and the Earth at your backside, say, and you can observe the other part of the firmament without the interference of the Sun or the Earth, without moving the satellite. And since everything goes about the Sun, you sweep the whole hemisphere or the whole sky in 1 year, say. So this constant geometry is also good for the communication. The communication is simple because you don't need to point the satellite, essentially. And the thermal stability of this neighborhood is very important also because you always at the same distance from the Sun and Earth and things like that. So the thermal stability of the neighborhood doesn't change. And also, for instance, in the case of the Earth-Moon, these orbits about L2 have been considered for a permanent link between space station at the hidden part of the Moon. This part, we could have a relay, and so we could communicate with something at the hidden part of the Moon. And as we will see also, they provide ballistic planetary captures, they provide Earth and transfer return trajectories. We'll be addressing this in some minutes, and they provide interplanetary transport also between, for instance, the moons of Saturn. And also, I'm not going to address this thing here, but also they are good places for formation flight, so for the observation of the for sets of satellites devoted to special missions of observations. So the first Liberation Point satellite was in 1985, and it was IEEC 3. Essentially, this is an artistic view of that mission. Essentially, it was launched from Earth, and it stayed for a certain time about L1, where it studied the Sun. The Sun is here, so the Liberation Point is here, and it was in an orbit about this point, and get data from the Sun, and after that it was launched and visit a comet and something like this. But for the moment we are mostly interested in this kind of trajectories, that going from the Earth, departing from the Earth, go to this Liberation Point regimes. Okay. Another popular satellite, actually currently in the Liberation Point regime, is the SOHO. You can address the web page. NASA, it's the Sky Watcher, and so prevents from the radiation of the Sun, and studies the Sun, takes data and prevents from these solar storms. So when SOHO announces the solar storms, all the satellites in low Earth orbits can be closed and to keep safe the instrumentation. This is in L1, in the L1 point. This is the Earth, and this is the direction of the Sun. And another mission is the MAP mission, the Cosmic Microwave Background Radiation, the by the way, this was the one that took the picture of the Big Bang. So this one, this satellite knows where the Big Bang is, and in fact the Big Bang is everywhere, no? Okay? Because it took, say, the picture. I'm not expert in cosmology, so maybe at least Emily knows much more about this, but from L2, the space, say the astronomical site in our universe, the spacecraft took the picture of the background cosmic radiation that is something related to the first times of the initial time of the universe in some way. So the anisotropy of this picture gives information to the physics in order to understand these kind of things. Okay. So the key of the question, the point of the question is the behavior of these orbits. So why are these orbits interesting for mathematicians? And essentially the explanation is here. If we consider, as you know, the eigenvalues of the Libration points, they are in this way. We have plus minus real quantity, plus minus imaginary, plus minus imaginary. So this means that essentially the Hamiltonian near in the neighborhood of these points behave this way. This is a saddle, and these are two center. So we will have near the Libration points, we have essentially in-plane oscillations, out-of-plane oscillations that can be coupled. These are uncoupled, but they are coupled when you add higher order terms. But essentially we will have Lissajous orbits. But everything is multiplied by this saddle. So it's a center, in-plane oscillation, out-of-plane oscillation, times the saddle. And the saddle makes these orbits very unstable, and this will be related to the control of the satellites. So we will have orbits. We have in the neighborhood of the Libration point, we will have orbits, but they will be very unstable. Another ingredient for our computations or for our visualizations are the Poincaré maps. The Poincaré maps are obtained when you place, for instance, a plane transversal to the trajectories. And you only plot the points where the trajectory crosses this plane. So this gives you information about the trajectories. For instance, in the Libration point regime, we have this thing here. This is the Poincaré map of about L1 for a given level of energy, say. And this point here corresponds to a vertical orbit. It's an orbit that goes north and south of the ecliptic and crosses this point here, and this is the result. At the same level of energy, we have another invariant curve, this one here, that corresponds to a Lissajous orbit, which is like a cylinder that crosses this plane here. And so on. With a bigger orbit, we have another Lissajous orbit. And the outer one in this representation corresponds to a planar orbit that is no longer here. So this outer orbit is in fact this one here that is completely contained in the plane. Okay. So by using things like this, we can represent the Libration point orbits. These are for a given level of energy, and for other levels of energy, so it means that taking the Hamiltonian to another level or the Jacobi constant that is the same, we find these different classes of Libration point orbits. We did these computations in 91. It was the first time that we could visualize the whole set of orbits corresponding for different levels of energy close to the ones of the equilibrium point. And so we have different kinds of trajectories. All the points, fixed points, correspond to periodic orbits. We have two halo orbits that I'm going to show in a minute. We have here another periodic orbit which corresponds to a vertical oscillation, and another one to Lissajous orbits, about the vertical one or about the halo orbits. To produce this picture was not easy. It was made by means of a normal form procedure that could reduce the Hamiltonian to the central manifold, and in such a way that the unstable part is skipped. So we only consider the orbits inside the central manifold, and so we can integrate the Hamiltonian without the instability. And the orbits we have before, just to show a little bit more, essentially the ones that we are going to talk today are these ones. These are the Lissajous orbits. Here you have more or less, I'm sorry, the view is not very good, but it's like a cylinder. These are the orbits that are in this region. These orbits are in this region. And orbits like this, that make an annulus, that are a Lissajous orbit about another periodic orbit which is a halo orbit. So essentially we have the 3D view of the orbits are these ones here, but how these orbits look from the Earth are in this way. So the Lissajous, this is how the Lissajous will look from the Earth. It's like filling a square in the way, and the halo orbits and quasi-halo orbits make like a torus. It's like when we see through this hole here. Okay, these have nice properties. This one has the property that when we put the sun in the picture, the sun will be, say, in the center of the. So these orbits avoid the sun. To avoid the sun is very good because the sun, the radiation of the sun hides the. Okay, the radiation of the sun hides the signal from the spacecraft. So it's important to avoid a zone about the sun, and so these orbits do this job. But these ones don't do this job because at some point the Lissajous orbit will cross the solar disk. Okay. So we also compute these kinds of orbits using the normal forms procedures and by means of listed Poincaré procedures that give us a very good approximation of these trajectories, and these approximations are obtained by means of expanding the equations of motions and looking for a solution in series of these equations of motion. For instance, this is the linear part of the solution of the linear part that gives you the key of the motion. I'm sorry, but this is not. This is we have here the unstable part. This alpha 1 is the unstable part. Alpha 2 is the amplitude of the stable part. And this is multiplied by a cosinus, which corresponds to the libration. So essentially, the cosinus and sinus terms correspond to the linear Lissajous orbit, while the exponential term corresponds to orbits that tend to the Lissajous or depart from the Lissajous, of course taking appropriate values of the constant. For instance, if we take these values here, alpha 1 and alpha 2 equals to 0, we have only the libration part. But if we take alpha 1 equal to 0 and alpha 2 different from 0, we have a stable manifold since we have only exponential terms with negative exponent and so on. Okay. So this kind of expansions can be down up to high order, and you can represent libration point orbits in this way, essentially, roughly speaking. And as I mentioned before, the second ingredient for the computations of our transfer trajectories are the stable and unstable manifolds. If we have a libration point orbit, in this case we have a Lissajous orbit, it's like a cylinder. We have the set of orbits that tend exponentially to this, asymptotically to this Lissajous orbit, and this make the stable, the set of the stable orbits that are in the stable manifold of this Lissajous. In the same way, we have the unstable orbits that depart from cylinder. Of course, these orbits can be used for transfer applications. And so I will talk a little bit. The purpose of this talk is to show a little bit all the things related to the transfer problem associated with the Libration point orbit. So, probably before talking a little bit about transfer, say that the starting point of this methodology, the starting point of the methodology of looking at the geometry of the orbits and essentially taking into account the natural motion and not the artificial one. I mean, the artificial one will be the maneuvers. And so in order to reduce the maneuvers, what we do is to take into account the natural motion and try that the dynamical system give us will solve us the problem as much as possible. So if the flow of the system goes in the way that you want to do the things, so take worth of this flow, and then you don't need maneuvers. Okay, so probably the first ideas in all this in this implementation were done by Gerard Gómez, Jaume Llibre, Regina Martínez, and Carles Simó in 1985, when they designed a station keeping procedure. So this is a way to maintain the satellite in the Libration point orbit by means of cancelling the unstable component. So this is a geometrical procedure that is not related to the common optimization procedures of feedback, things like this. So probably this was the starting point of using this kind of ideas in emission design for a specific astrodynamic applications. And from this, using similar ideas, we can address different kinds of transfers. For instance, we can address impulsive direct transfer from the Earth to the LPO, to the Libration point orbit. Low thrust transfers to the Libration point orbit. So we can transfer inside the L1 or L2 regime, and in this way we can change the size of the orbit. We can change the phase of the stacks of satellites. We can do eclipse avoidance. We can transfer from L1 to L2 regime or vice versa. Or we can transfer between regimes in the Earth-Moon system, from the Earth-Moon system to the Sun-Earth system, or vice versa, things like that. So we have a plethora of different kinds of transfers that we are going to see at least a couple of them, and how things can, the more simple ones, say, in which way can be addressed. For instance, if we have here a Libration point orbit, this is a Libration point orbit, and we have an orbit about the Earth, how can we transfer? This way, so the natural idea is that let the dynamics do the transfer. So if you choose an asymptotic orbit, an orbit on the stable manifold, and you can inject here in the stable manifold, then the stable manifold gives you the transfer to this orbit. Okay. The same idea. So here we have a visualization of the whole stable manifold for a Hell orbit. So if we take any of these, we will go in a free way to the Libration point orbit. So essentially the idea is to compute, not to look in any orbits and just a means of try and error. So essentially what we want to do is to compute this kind of these manifolds, and to select the most appropriate one for the transfer. This can be done for both, for periodic orbits or for quasi-periodic orbits. Of course, the technical things are more complex for quasi-periodic orbits, but the idea could be the same. Also, we could design low thrust transfer. So in the low thrust, you have a small thrust that rises the perigee of the satellite, and so to the point that it escapes from the Earth. In this case, in this example, the thrust is aligned with inertial velocity in order to maximize the rate of change of the semi-major axis. And at some point here we stop the thrust because we merge this orbit with the manifold. So at this point they coincide, and so you stop the thrust, and the manifold gives you a free transfer towards the Libration point orbit. So, for instance, in this case we have the orbit spiraling about with a low thrust. We have our orbit spiraling about the Earth. This is the way. And now we switch the thruster off, and so we are inside the manifold, and we have the transfer to the halo orbit. So how do we do these computations? Usually we proceed in the other way around. We take initial conditions in the stable manifold, and we integrate backwards these initial conditions. And after some time we add the thrust in the other sense, and then we approach the Earth. At some point, and when we do this, we can explore the parameters in order to see if they are suitable transfers or not, things like that. So, for instance, in this case, we are interested in low eccentricity and low inclination departure, fixed parameters for the departure. In this case, we're taken 1,000 kilometers and so on. Okay. So essentially, we compute these manifolds, and then since we know that these will be the best ones for the transfer, this way you propagate these manifolds, and then you can obtain the suitable ones for the transfer according to the needs of the mission. Okay, and this is a procedure that it's implemented in most space agencies and since the work we did in the 90s. Okay. For instance, another case that can be addressed is the problem of eclipse avoidance. Eclipse avoidance, for instance, we have here is a representation of the Sun, and this is the Earth, okay, and this is say L1, okay. So L1 will, if you see the Sun from the Earth, on an elevation point orbit here, located in the middle of the way, you will see something like this. So the Sun will be like a disk at this place. So this means that this least trajectory, Lysage's trajectory, will cross the Sun at some point. Okay. However, if you use a halo orbit, a periodic orbit, you avoid the Sun. The Sun is in the middle, in the satellite. The problem is that this size here is very long. It's of the order of this part is of the order of 600,000 kilometers, while for the Lysages you can choose any size. For instance, 120,000 kilometers, which is much more suitable for communication purposes. So if we want to place a satellite here, you will need to avoid the exclusion zone at some point. And one way to do this in the dynamical system approach is the following. So using these procedures, we avoid the optimization computations, which are more related to black boxes than to dynamics. And this will be implemented in the Gaia mission. Okay. So essentially, is the cylinder of orbits, for instance, the Lysages, can be considered, since the amplitudes are fixed, so the actions of the orbit are fixed. You have only to bother about the angles of the representation of this orbit. And so if you consider the angular representation, the in-plane frequency related to in-plane frequency, and the one related to the out-of-plane frequency, a torus can be represented just in a square, where you have 2 pi and identify the edges. Okay, and each point here, position and velocity, each state corresponds to a point there. But the nice thing is that in these trajectories, in this representation, the exclusion zones, well, are more or less like ellipses. They're not ellipses at all, but we could take here just ellipses a little bit bigger. Okay. So they are seen as holes here that correspond to these places. Okay. And the trajectory is a straight line, because we are moving in a torus, and in this kind of coordinates, the trajectory is a straight line. It's moving in a uniform speed. And the thing is that, well, the slope, as we were going to see, is just slowly less than 1. And so the trajectory moves this way until it hits the exclusion zone. Okay. This means that you see the ratio, the slope of this trajectory depends on the ratio of the frequencies, which is very close to 1. both for L1 and L2. In L2 we have also a radius of exclusion radius is of the order of 14,000 kilometers related to the eclipse of the Earth. This is why we need also to avoid a region at L2. So if we place the satellite, say here, the motion in this point of the Lissajous orbit, the motion goes this way until it hits the exclusion zone and gives you, say, 5 years free of eclipse. But when you hit the exclusion zone, then you need to do a maneuver in order to avoid it. And using the dynamical systems method, just looking at the questions, this can be represented in this way. It's a jump from B to C, which corresponds just to a maneuver. It's a maneuver that can be computed, say, in an optimal way, but moreover, the optimal solution corresponds to a symmetry line in the plane of in this plane representation. And so we have two ways of avoiding the exclusion zone: is with in-plane maneuvers and out-of-plane maneuvers. And this can be, these maneuvers can be obtained just by means of analyzing the equations and without optimization procedures. And essentially what these kind of maneuvers, what they do, and you see here in the Lissajous we avoid the exclusion zone, the least moves. Essentially what is happening is that the maneuver at some point is here, injects the satellite into the stable manifold of the same orbit, but it turns out that this stable manifold crosses in position, crosses the same Lissajous. So what we are computing essentially are the places where the manifold crosses the orbit itself. Okay. Well, another ingredient or another case that's very interesting is related to the homoclinic and heteroclinic connections. The first time that these kind of things were used were in the Genesis mission of the NASA Space Agency. This is the spacecraft. The Genesis spacecraft was designed, and this was the advertisement of the NASA, in order to catch a piece of the sun. Okay, so the piece is very small, a rather small piece, and in fact it's just the radiation of the sun, the microparticles. Should be encrusted here in these canisters of the satellite. So the satellite was in the Libration point regime. At some point, open the canister. It catches some pieces of the radiation of the sun inside this golden. Well, these are gold pieces. Okay. And so then the canister was shattered, and then everything should have to be delivered at the Earth, towards the Earth. So the Genesis mission has this nominal path. So this is departure from the Earth, stayed for 4 rafts about Libration point orbit, and then in order to be captured at daylight, because the mission had to be ended using an helicopter when the satellite was descending. It went close to a heteroclinic connection to orbits near L2, and then in just a phasing loop in order to get good entry conditions. And so this is essentially a free ride. Since the satellite was launched, everything is it's free of maneuvers. So there is no delta V at all. Essentially, of course, for TCM. TCM is the ones that are listed here, the trajectory correction maneuvers. Okay. This is the 3D profile. This is we launched from here. You stayed here catching the particles of the sun, and then we were back delivering the particles towards the Earth. Well, the recover, as you have in this picture, had to be done by the stuntmen of the Hollywood Studios in a Utah camp of the army in the States. But the thing is that the helicopter couldn't catch the capsule at the end, and the capsule, this is the final shape, broke because well, it was a collision with the Earth. Okay. At that time, I'm going faster. So at that time, we had more or less regular telecons with a team and the responsible of the Genesis, the trajectory of the Genesis mission in Pasadena. And when this happened, the silence, we had silence for 1 week, a terrible silence. So, and after say several days, the NASA headquarters congratulated us for everything, because the trajectory was right. I mean, the satellite impacted at the right place. The thing that was wrong was the problem with this part of the capsule, the upper part, should have to be jettisoned because need to deploy the parachute, and the explosive related that should have to do the work didn't work at that point. It was a problem of Lockheed Martin. So it was, but the trajectory was right. So okay, the trajectory was right, and so nobody talked about the trajectory, of course, but everybody talked about this. Okay. And this is another interesting heteroclinic connection between L2 and L1. This was sent me by Dave Folta, which is the responsible of the Artemis mission at NASA Goddard. And so it's Artemis came from here, and after some roughs near to a heteroclinic connection was near. It was near to the moon in order to study the moon and the influence of the sun across the moon. So this is very interesting to study this kind of trajectories. And these trajectories, this was a little bit the subject of this talk, are related also to a level of energy that we have a situation like this. With the Jacobi constant, it turns out that for a given level of energy, for a given Jacobi constant, the position of the satellite or the position of a comet in the solar system cannot be arbitrary. There are in some cases, for some levels of energy that correspond essentially to the cut of this function, the omega function. We have regions that the motion is forbidden. So for a given level of energy, this region here, it's known as the Hill region, is forbidden. So the satellite cannot be here. So if the satellite has to cross from, say, the outer part to the inner part, here is the Sun-Jupiter case. But if we go from the outer system to the inner system, you have to cross this bottleneck. Is the only way. And it turns out that this situation is the common one in our computations. We have always this kinds of structure in many situations. So this is very important. And the thing that the way these gates are governed are essentially due to the manifold related to these libration point orbits. Okay. Yeah, that one I would like to tell something about this, but I think I have no time. But just to say that, the study of how these things are connected, I mean, this interior and this transit or non-transit orbits are present, and how they behave in a topological and geometrical way. Well, the studies are mostly devoted to Conley in 1968, and to McGehee, which gave us another topological representation. And following Conley and McGehee, there is the work of Jaume Llibre, Regina Martinez, and Carlos Simon in 1985. And later, this was essentially here in these places, they found that there are homoclinic connections. Homoclinic connections mean orbits asymptotic, both in forward time and backward in time to the same libration point orbit. And here in this work, they show the transversality of the intersections of the manifolds, and also that in the Poincaré sections we have cycles. But essentially, this work here was popularized by people of Caltech in the design of missions, and then we contributed also in the design of 3D, in the 3D case, because all these parts here were done in the planar problem. Okay. Well, essentially, what we look is that the essential part here is the manifold related to, for instance, two periodic orbits. Assume that we have a planar case and we have a planar Lyapunov here and a planar Lyapunov here. If we want to transfer from one to another with a zero cost, we need to put the satellite in the unstable manifold of one orbit and in the stable one, both in the stable one as the other one. Okay. And it turns out that the intersection of these points are the ones that give the free ride, the free transfer. Also, the other regions have other topological meanings. I mean, the other regions, the regions that are inside these curves, depending these three regions here have different topological meanings that I have no time to explain now. But there's a way to design this kind of trajectories. I'm going to skip this. This was essentially the 2D case. Also, these kind of things can be, say, generalized some way, in not trivial way, but in the 3D case. For instance, when we connect two Lissajous orbits, we are looking of intersections of manifolds of three spheres that are normally parabolic. One way we have this Lissajous orbit is a 2D tori inside a 3D sphere, and here we have another one. They are hyperbolic, and well, you are looking for connections of the manifolds of these two objects, and you can obtain families like this. And finally, well, as we talk about the patching conics, here in this kind of regime we have the similar idea, which is the idea of patching RTVP models. For instance, we can consider Sun-Earth and Earth-Moon, because like two uncapped, in principle, two-body problems, three-body problems. And why is this useful? So it's useful, for instance, to place a gateway station between the Moon and the Earth to give service to satellites and in the Libration point regime of the Sun-Earth. It turns out that the Libration point regime in the Sun-Earth and the one in the Earth-Moon system are very close to in terms of energy. And so, in fact, there are phi transfers from one to another. And here we will see some one. So this is a way to patch a Libration point orbit here with some Libration point orbit in this way about the Sun. Wow. So I'm going to finish this. I'm going to show you just some. Let me see. No, this was the first time. These are some computations about this kind of orbits. We have an heteroclinic orbit from a Libration point orbit about the Moon and a Libration point orbit about the Earth. This was the precursor. The same ideas can be used to transfer to the Moon. And of course, this gives us. This has been popularized in what is known as the interplanetary superhighway, which is it's not a concrete concept, but in some way it tells you that you can move in the solar system, say almost for free. It's not true at all, but almost for free, but takes a long time. Okay, so long that. And of course, this kind of things appear again in the mass media. This is a picture of Caltech, and I'm going to skip it. And there are also applications of this in dynamical astronomy, essentially related to the formations of the arms of the galaxies. Here we have some representations of the arms of the galaxies and the manifolds that could produce these orbits. And with this, with people of Marseille, we produce a new theory for the formation of these arms, different from the one in astronomy that has been the most common one in the last years. And finally, well, my presentation tried to follow a line, yeah? But there are many people who has contributed in different aspects to this single line that I've been doing. And so if we go a little bit farther from this line, we find many people from Barcelona, and especially here related to more theoretical things, and many people related to more, say, practical things about astrodynamics, and people of aerospace universities and so on. These are just a few lines, but probably are the closest to my talk. Okay.